Okay, so let's start with a very simple problem uh, on special relativity. So we have a inertial frame fixed to Earth, and suppose there is a spaceship which is moving with a velocity v with respect to Earth, and we assume that both these systems are inertial systems, inertial reference frames. And suppose inside this spaceship there is a charge, say q, and this charge is performing small oscillations because inside this spaceship there is some charged plate from which there is an electric field coming out, and this electric field is interacting with this charge, and because of small oscillations it is performing simple harmonic motions. Okay, so inside this spaceship you have this charge which is performing a simple harmonic oscillation, and the question is that what is the time period of this oscillation in the frame of reference of the spaceship, and what will be the time period of this oscillation for an observer standing on Earth, meaning an observer standing in this inertial frame connected to Earth. So let's begin our solution. Um, so we already know some things about simple harmonic motion, if we have a simple massive object performing SHM on Earth under influence of gravity, we see that this is equal to simply 2 pi root L by g, where g is the acceleration experienced by the mass for some mass on Earth. So we can see from this formula already that what matters here is the acceleration experienced by the bob. So in our case, since we have a charge, so what is the force acting on this charge, which is F is equal to EQ. And yes, this charge also has some, this object also, this bob also has some mass. Okay, so suppose mass is m. So what we need to effectively calculate is the acceleration due to this electric field. So mass into acceleration is equal to EQ, where E is the magnitude of the electric field. So from this we get A is equal to EQ by M. So we put this into our formula and we get 2 pi root L by EQ times M. Okay, and uh, in our spaceship, which is our frame of reference, in this frame of reference, this is the time period experienced by the bob, our bob. It has also some charge and some mass. This now, this problem may seem very confusing if you go in a very dynamical kind of way, where you go to the frame of Earth and try to calculate every dynamical quantity. Suppose this is the frame of Earth and you want to calculate everything like mass, so you will need to, in order to calculate the time period, you again need to know the acceleration, how the charge changes, how the length is changing, how the mass is changing. So all these factors, how do they change, and depending on, like, if it is uh, if this is a rectilinear motion, v, or if it is like no, it is rectilinear, but what I mean to say is that whether um, it is moving linearly away from along y direction, or is there some um, motion towards the z prime direction. Wait a second, I think I made a mistake. Yeah, this is the frame of earth. Okay. Yeah, so mm, so doing all that is very complicated. You also need to know how the electric field changes, how the length changes, how the mass is changing. Everything is changing. So doing a dynamical calculation by using Newton's equations by first transforming all the dynamical quantities is going to be very complicated. But relativity saves us from all these calculations because we already know that how time transforms, because we already know time, like Lorentz transformation. uh, so we have t prime t. So because we already know the formula for time dilation, which is given by t is equal to uh, v square by c square. And since we already know this, say this is t prime, so we simply need to plug this in and just write 2 pi root Lm by eq 1 minus v square by c square. So the time period observed by the observer is t is equal to, and yeah, so that's it. So if you repeat what I was going to say, that you have a inertial frame connected to earth, and there is a rocket which is going with some constant velocity with respect to earth in a rectilinear fashion for now, and there is a charge particle which has some mass m, and some length of the string is l, and you have some electric field due to some charge plate inside the spaceship, which is producing this constant electric field. And the question was, what is the time period observed by an observer on earth uh, for this pendulum in this spaceship? So we simply plugged the well-known formula here, but you can also instead solve the dynamical equations, and you will get the equation of a simple harmonic oscillator. And by looking at it, you can actually read the um, time period, because you will have a equation which tells about the angular velocity. So from that you can read the time period. So we plugged this, we solved this Newton's equation in the spaceship and got an acceleration inside of this charge inside the spaceship, and we have this t prime is equal to t from the from our calculations inside the spaceship, and then we simply used the Lorentz transformation for time instead of calculating um, all the transformation of these dynamical entities like length, mass, electric field. We don't need to do all that dynamical calculations. We can simply understand how time works and get an answer which is correct. So thank you.